Jai Hind, ladies and gentlemen. Very warm greetings and welcome to each one of you. It gives me a great pleasure to share a video presentation on upset prevention and recovery technique with you all. DGCA Ops Circular number 6 of 2018 on upset prevention and recovery technique was issued on 15th October 2018. The circular mandates UPRT flying and ground training for all the pilots. UPRT syllabus is vast and the entire contents cannot be covered in one video. Hence, around 5 video presentations have been prepared. I am sharing the first video presentation on UPRT. Other videos will follow suit. So here we go. First, we shall discuss what is aeroplane upset. An aeroplane in flight unintentionally exceeding the parameters normally experienced in line operations or during training and defined by the existence of at least one of the following parameters. First one is pitch attitude greater than 25 degrees nose up, pitch attitude greater than 10 degrees nose down, bank angle greater than 45 degrees. The aircraft may be within the above parameters, but flying at speeds inappropriate for the conditions. Now we shall discuss loss of control in flight. The term loss of control in flight is a categorization of an accident or incident resulting from a deviation from the intended flight path. Analysis of loss of control in flight accident data indicate that contributory factors can be categorized as being either aeroplane systems induced, environmentally induced, pilot induced, or any combination of these three factors. The pilot-induced accidents are the most frequently identified cause of the event. May be due to application of improper procedures, including inappropriate flight control inputs, one or more flight crew members becoming spatially disorientated, and poor aeroplane energy management. One or more flight crew members being distracted, improper training, intentional low flying, heavy airplane wake and clear air turbulence, severe weather turbulence, and icing conditions. Now we shall discuss threat and error management. Now, threat and error management is a method used to help maximize safety margins and minimize risks by first identifying threats to successful operation accomplishment and then determining ways to mitigate or eliminate the identified threats. The threat and error management concept is to have pilots consider not only the external influences that impact safety, but also to consider their own reactions to those influences as well as mistakes they make in the conduct of a flight. Now we shall talk about threats. Threats are those events that are beyond the control of the pilots, which increases flight complexity, requiring flight crew management and attention. Threats are further divided into expected and unexpected. Forecast weather, planned routing, and high density airport operations are all threats that fall into the expected category. The pilots can plan for these issues and plan defenses to accommodate them. Aircraft malfunctions, changed routings, and unforecast weather issues fall into the unexpected category, and pilots must deal with these issues as they emerge. Threat management involves how the pilots anticipate, prepare for, and respond to these threats. The pilot's pre-flight inspection of the aircraft, the use of the checklists, and adhering to operational limitations all help prevent aircraft malfunctions. A thorough weather briefing, use of airborne weather radar, and periodic in-flight weather updates are all parts of managing threat due to weather. Now we shall talk about errors. An error is any act committed or omitted by the pilots that results in a deviation from what they intended, reduces the margin of safety, and increases the likelihood of an adverse operational event. There are three categories of errors: procedural, communications, and aircraft handling. Procedural errors involve pilot divergence from policy, regulations, aircraft flight manual standards or procedures. Examples include accidentally missing a checklist step or purposely omitting said step. Communication errors can be between the pilots or with those outside the cockpit. Aircraft handling errors are identified as those involving skill or knowledge in handling the aircraft. Aircraft handling errors result in deviations of aircraft direction, attitude, velocity, and configuration. How the pilot responds to an error directly impacts the outcome of the event. First of all, the error must be detected. An error that is not detected cannot be managed. If the pilot detects the error and the error is managed appropriately without additional error and without significant effect, the error is said to result in a trap. That is, the error has been trapped. Exacerbate is the result of the pilot's response or intentional non-response to a detected error, resulting in the situation worsening. Finally, if the pilot does not react because the error is not noticed or is ignored, it is classified as fail to respond. There are three possible outcomes from the error, regardless of the response of the pilot. If there is no impact on the safe conclusion of the flight, regardless of action or inaction by the pilots, or even if the error was undetected, the outcome of that error is inconsequential. The pilot, in responding to this error, might commit an additional error, and that error must also be detected and managed by the pilot. Third and most critical is the pilot's response, which may result in an undesired aircraft state. Now we shall discuss undesirable aircraft state. Undesirable aircraft state is position, condition, or attitude of an aircraft that clearly reduces safety margins and is a result of actions by the flight crew. The error results in the aircraft being unnecessarily placed in a condition that increases risk. This includes incorrect vertical or lateral navigation, unstable approaches, low fuel state, lining up for wrong runway, and reduced separation. The term undesirable aircraft state encompasses a wide range of situations. Being at the wrong altitude constitutes an undesirable aircraft state. If deviation in pitch, bank, or airspeed becomes severe enough, the undesirable aircraft state moves into the category of an upset with an accident or incident resulting from an upset event falling into the classification of a loss of control in flight. In response to the undesirable aircraft state, the pilot may apply appropriate techniques and strategies to mitigate the situation, or the pilot may make control inputs that create further deviation from the desired aircraft state and exacerbate the situation, or the pilot may fail to respond. The outcome of an undesirable aircraft state can be the recovery of the aircraft back to the desired aircraft state, an additional error that must be further dealt with by the pilot, or an accident or oblique incident. Pilots can be trained to appropriately manage undesired aircraft state through upset prevention and recovery technique training. Now we shall discuss how we can integrate threat and error management and upset prevention and recovery techniques. Pilots can significantly increase flight safety by integrating UPRT considerations into their TEM process. By including the threats that can result in a loss of control in flight event during the flight planning phase, they can develop plans that avoid those threats. By keeping loss of control in flight threats in mind, during the conduct of the flight, the pilot will be more likely to recognize the precursors to a loss of control in flight and take early action to prevent a loss of control in flight occurrence. Should a loss of control in flight event happen, having participated in a quality UPRT program, that is training program, which is very important, which should have imparted the skills necessary to recover the aircraft. So here emphasis is on quality UPRT training. Threats that can be anticipated should be taken into consideration during flight planning. Forecast weather that includes thunderstorms, wind shear, or icing all fall into this category. Wake turbulence also has a component that falls within this category. If the flight plan includes operations in areas where heavy air traffic is expected, the pilot should take this into consideration during planning. The pilot, with an awareness of preceding traffic, the airfield winds, and the dynamics of wake turbulence, can plan the approach to minimize the possibility of encountering wake turbulence. While the best mitigation is to avoid the threat completely, oftentimes the flight is of such priority that other forms of mitigation are necessary. During flight, pilots should continue to be aware of emergent loss of control in flight threats. By staying aware of possible situations conducive to loss of control in flight, the pilots are more likely to recognize the early stages of a loss of control in flight event. Early detection greatly enhances the likelihood of preventing an upset. This awareness is especially important during flight with the autopilot engaged. It is possible that the pilot will assume a lower level of vigilance if the flight is on autopilot, but in the presence of a loss of control in flight threat, such a relaxed attitude can lead to a sudden upset. The autopilot will attempt to keep the aircraft within the desired state using more and more of its control authority. If the limits of authority are exceeded, most autopilots will disengage suddenly, allowing the controls to return to neutral in most aircraft. The counter upset control inputs previously held by the autopilot will be removed and the aircraft may be rapidly placed into an upset condition. A vigilant pilot would notice the increasing displacement of the control from neutral. In such an instance, it may be prudent to assume control from the autopilot to prevent the situation of experiencing a disconnect with no pilots on the controls. A further byproduct of active awareness of loss of control in flight threats is that the pilot is less likely to be startled should an upset occur. A pilot who is unaware may have as much as twice the reaction time as that of a pilot who is aware of the potential need for intervention. Minimizing reaction time in a loss of control in flight recovery event is very essential. A research has shown that the window of opportunity available to resolve an airplane upset is often less than 10 seconds to initiate correct recovery action. With this potentially limited recovery window, pilots should constantly remain vigilant awareness, and active mitigation of loss of control in flight threats. Now I shall refresh your memory about some aerodynamics. Now, in this figure you see the forces acting on an aircraft in level flight: lift, weight, thrust, drag, center of gravity, and center of pressure. These are the four forces that act on an aircraft in flight: lift, weight, thrust, and drag. The motion of the aircraft through the air depends on the size of various forces. Lift and drag are aerodynamic forces that depend on the shape and size of the aircraft, air conditions, and flight velocity. Lift is directly perpendicular to the flight path, and drag is directly along the flight path. The ratio of lift to drag is an indication of the aerodynamic efficiency of an aeroplane. An airplane has a high L/D ratio if it produces a large amount of lift and a small amount of drag. Under cruise conditions, lift is equal to weight. A high lift aircraft can obviously carry a large payload. Under cruise conditions, thrust is equal to drag. A low drag aircraft requires low thrust. An aircraft with a high L/D ratio can carry a large payload for a long time and over a long distance. This figure shows changes in lift and drag coefficient with change in angle of attack. In the figure you can see how the lift coefficient keeps on increasing as the angle of attack is increased till the aircraft reaches to a stalling angle of attack. Thereafter, the lift coefficient starts dropping. The drag coefficient is gradually increasing, and as the angle of attack is increased, and it is a very high value at very high angle of attack. These figures show comparison of L/D max jet and propeller driven aircraft, thrust and power required with increase in speed. This figure shows effect of speed on components of drag. As can be seen from the figure, induced drag is high at low airspeeds, and as the speed is increased, it keeps on reducing. Induced drag is directly proportional to 1 by v square. Profile drag increases very gradually, but parasite drag increase directly proportional to v square. That is, as the airspeed keeps on increasing, parasite drag keeps on increasing to very high levels. You also see the total drag curve and minimum drag or L/D max. That is this place. This figure shows changes in lift, drag coefficient, and L/D with angle of attack. Lift, drag, and the L/D max. This figure shows the total drag induced drag, and parasite drag. With increase in speed, what effect takes place on the induced drag, parasite drag, and total drag, and also stall speed is also shown in this picture. Now you can see in this picture the forces acting on an aircraft. L by D is equal to lift or drag. Lift is equal to CL half rho square S. Drag CD half rho V square S. So high L by D means high efficiency, long range. Also high L by D can carry large payload and low fuel consumption. The lowest point on the total drag curve is known as the L by D max. The speed range slower than L by D max is known as slow speed, which is sometimes referred to as the backside of the power drag curve or the region of reverse command. Speed faster than L by D max is considered normal flight or the front side of the power drag curve. Normal flight faster than L by D max is inherently stable with respect to speed. When operating in level flight at a constant airspeed with constant thrust setting, any airspeed disturbance such as turbulence will result in the airspeed eventually returning to the original airspeed when the total thrust has not changed. Slow flight slower than L by D max is inherently unstable with respect to speed and thrust settings. When operating at a constant airspeed with constant thrust setting, any disturbance causing a decrease in airspeed will result in a further decrease in airspeed unless thrust is increased. The lower speed will subject the airplane to increased drag. This increase in drag will cause a further decrease in airspeed, which may ultimately result in a stalled flight condition. Flight slower than L by D max at high altitudes must be avoided due to the inefficiency and inherent instability of the slow flight speed range. When operating slower than L by D max and where total drag exceeds total thrust, the airplane will be unable to maintain altitude, and the only remaining option to exit the slow flight regime is to initiate a descent. External factors such as changing winds, increased drag in turns, turbulence, icing, or internal factors such as anti-ice use, auto throttle rollback, or engine malfunction or failure can cause airspeed decay. Heavily damped auto throttles designed for passenger comfort may not apply thrust aggressively enough to prevent a slowdown below L by D max. Pilots must keep this factor in mind. Slower cruising speeds are an issue. As airplanes are pushed to more efficient flight profiles to save fuel, it may dictate high altitude cruising at lower Mach numbers. The net result is the crew may have less time to recognize and respond to speed deterioration at altitude. At all times, pilots must ensure that flight slower than L/D max is avoided in the high altitude environment. Proper flight planning and adherence to published climb profiles and cruise speeds will ensure that speeds slower than L/D max are avoided. Airplane manuals and flight management systems produce optimum climb speed charts and speeds. When increased rate of climb are required, pilots must ensure speed is not decreased below L/D max speed. Evidence shows that inappropriate use of vertical speed modes is involved in the majority of slow speed events during high altitude climbs. Thank you very much, ladies and gentlemen, for sparing your precious time to watch this video presentation. Number of fatal accidents have occurred due to the inability of the pilots to recover from unusual attitudes. Hence, it is essential that all the pilots are knowledgeable and aware about the various factors which can lead to unusual attitudes, and they should also know the correct recovery procedures. Remember, knowledge and awareness is safety. Hope you found this video useful and interesting. Wishing you very happy and safe flying, many happy landings, and a very happy, prosperous and safe 2022. Jai Hind.